discussing about methods to estimate the reliability of the system. And as a review, let's define again the problem that we try to solve. We have information about the probability distribution of all input random variables, and we want to find the probability of failure of a component. We learn how to estimate the probability of components of systems using three methods. The first one is integration, and we talked about the conditional probability theory. The second one is Monte Carlo simulation, standard Monte Carlo simulation, and the third is variance reduction techniques. When we use Monte Carlo simulation, we need a random number generator that generates random numbers from a given probability distribution. So if you know the probability distribution of the thickness, for example, of a plate, then you draw random numbers from that distribution, and then you use them to calculate the probability of failure. Now, when you use Monte Carlo simulation, it's important to quantify the accuracy of your estimates. So you get a probability of failure, which is an observed relative frequency of failure. But that's not sufficient. You have to know also how accurate this estimate is. This is important, especially when the computational cost is very expensive. You don't want to spend more resources, more computational time to calculate more accurately probability of failure that is sufficiently accurate already. So it's very important to have an indication when you get a number, an estimate, how accurate it is. Okay, again, we have a performance function that is a function of properties of the system. The load that is applied, the material properties, etc. And that function, if it is positive, it means that the system survives. We can think that the demand is lower than the supply in a way. If the strength corresponds to the supply and the capacity corresponds, and if the capacity corresponds to the strength and the load corresponds to the demand. If zeta, this function is negative, then you have failure. And the limit state is when zeta is equal to 0. So if you have this plot here, which is conceptual, you have a region where the performance function is negative. There you have failure. If there in this region, you have failure. In this region, the strength is greater than the stress, so you have survival. And then on this line is the boundary between survival and failure. Of course, for practical purposes, you don't want to have a design that is here because it's very easy for any small perturbation the system to fail. Okay, conceptually, if you have two variables, the demand or stress and the capacity SU, then you have a joint probability density function, which is this surface here, okay? The higher values are more likely. Now, this is the range of values is divided into two regions. This is the failure region where the stress falls short of, is higher than the strength, okay? So the strength is not enough and the system fails. This is the failure region. And the survival region is the other portion. So you want the probability that you will have a combination of values of strength and stress in this failure region. This probability is a volume, is the portion of the volume under this curve that is in this region, in the failure region. So if you think about cutting this surface at this point, with this line, with this plane, with a plane, then this volume is the probability of failure. That's conceptual. One equation that you can use to calculate the probability of failure is this. Essentially, this is a calculation of the volume under the failure region where the performance function is 0. We have here an example of a case where we have overlapped the capacity or ultimate stress, which is the blue curve, and we have also the demand, which is the red curve. When we have an interference in this region, then failure occurs. Okay? That doesn't mean that the probability of failure is this area, as we said. But any point here corresponds to a scenario that leads to failure. The probability of failure is given either by this equation or equivalently by this equation. This equation is essentially the integral of the cumulative distribution of the capacity multiplied by the probability density function of the demand or stress. And in general, it can be from minus infinity to plus infinity. So this first term, the cumulative distribution of the strength, is the conditional probability of the strength being less than S for a particular value of S. And then if you integrate over all possible values of S, then you find the probability of failure. Okay? How about the second equation, which is equivalent to the first? What is this term? 1 minus the cumulative of the stress. Yes?
Probability of survival? Reliability?
No, this is the probability of the stress being less than a value. Okay, that's the probability of the, I'm sorry, this is the probability of the stress exceeding a value. F of S, capital F of S is the probability of the stress being less than the value. This is the complement, so it's the probability of the stress being higher than value S. And then this is the probability density function of the strength evaluated at this value of the stress. Okay, and if you integrate this, then you find again the probability of failure. All right, now the integral is not easy many times to calculate, especially if you use numerical integration. So you want to integrate, instead of integrating from minus infinity to plus infinity, which is very inefficient, you find the region for which the two probability density function overlap. So in this case, you'll see that the densities are very small in the range from outside this range, from 300 to 700. So the chance that these values, you have values in this range or in this range is practically 0. So instead of integrating from minus infinity to plus infinity, you can integrate from 300 up to 700. And essentially, captured all the probability mass and estimated the probability of failure quite accurately. So this is the first approach with the total probability theorem. Here is an example where the stress is normal and the strength or ultimate stress is quite good. We did that example. And here is the probability density function of the difference of the strength minus the stress, and if this difference is negative, then you have failure. So this area here corresponds to the probability of failure. We also talked about the safety index. If the stress and the ultimate strength are normal, then the safety index tells you how many standard deviations away from zero is this is the mean value of the difference of the strength and the stress. Okay, so this is the mean value of the difference. And remember, we don't want the difference to be negative because you will have failure. So this is the mean value of the difference, but because the difference of the two is random, it can assume values in this range or in this range. Now, if you fall below zero, you have failure. So this margin, which is from zero to the mean value of the difference, normalized by the standard deviation of the difference, is called safety index. And that can be 1, 2, 3, 4. The higher, the better, okay? Now, in general, to calculate the probability of failure, you integrate the probability density function of all the variables in the region where the performance function is negative. So you find the volume below the joint probability density function in this region. One approach that we use is Monte Carlo simulation. And there are two versions that we learn. One is standard Monte Carlo, where you simulate, you draw values from the true probability distributions. And the other is important sampling, where we draw values from other distributions that cause more failures. So let's review what we did about Monte Carlo simulation, standard Monte Carlo simulation. The idea is to generate on the computer sample values of all the variables, test for every combination of values if you have survival and failure, and then the relative frequency approximates the probability of failure. This is a pretty intuitive approach. So this is a flow chart of how you work about this. The first step is always define the problem, and that's a very important step. Define the problem means what you know and what you want to find, because you really understand what you know and what you need to find. In order to solve the problem, you have to have a model of the system that tells you when it survives and when it fails. You have to know or estimate the probability distributions of the random variables. If you don't have this information, you cannot proceed. Okay? Once you have these two steps done, then you generate sample values of the random variables. And you do, say, n replications, capital N replications. That means you generate n groups of random variables, and you check the design for each group. So you calculate the performance function to check if the system fails or survives. And the probability of failure is the relative frequency of failure. Failures over the total number of replications. Now, you got a value here, but this value is just an average value, an average frequency of failure. That doesn't tell you the whole story. You have to know also the accuracy of this estimate. And since you don't know the true probability of failure, you can calculate the standard deviation of the probability of failure. And then, based on the standard deviation, you will decide if it is accurate. Okay? If the standard deviation is 50% of the probability of failure, that's not good. You have to do more replications. It got to be something like 5% to 10% of the standard deviation, 5 to 10% of the probability of failure. Okay. You can perform Monte Carlo simulation depending on the complexity of the problem on using different software. If you have a small problem, like just a couple of variables, like stress and strength, you can use Excel or MathCAD. Bigger problems, you may have to use a finite element program to do that. Okay, so let's see some examples using Excel. So here is a simple example. We want to calculate the probability of failure of a system when we know the strength. We know that the ultimate strength is normal with a mean value of 97,600, standard deviation 13,900. That's the strength. And then the stress is normal with this mean value 97,600 and standard deviation 300. Okay. So we generate random numbers. First, we generate, as an example, 10 random numbers for the stress. Okay. Let's see. This is, we calculate the mean value of these numbers in order to make sure that the random number generator is correct. So the mean value is about 97,000, so that's okay. The standard deviation is 4,000. Maybe these values like this that are written there, they don't look right. The statistics. Let me check with other values. 100. Okay, the spreadsheet unfortunately needs to be updated. So the mean value of the strength is 97,600. I'm sorry, the stress. The standard deviation looks like about 4,000. The stress, that's the stress. The strength is this mean value, the standard deviation. Okay, and we have 10 numbers for stress, 10 numbers for strength. We have the difference. Now, if the difference is positive, there is no failure. If it is negative, you have failure. Now, based on this, there are no failures are observed. So this is a good sign, but the probability of failure cannot be zero, right? So we need more replications. If we do 100 replications, this is the these are the 100 replications. We calculate again stress, strength, difference, and then the failure index. And I think I see one failure, 2 failures. Well, there is a total of 3. Okay, this is 3. So we have 3 failures in 100 replications. So the probability of failure, the estimator of this is 3%. Doesn't mean again that the probability of failure is 3%. That's just an average value. It's the predictor that we have from 100 replications. And the standard deviation is almost 2%, the standard deviation of the probability of failure. Okay? So this is, we are using this equation with the square root of the product of probability of failure times probability of survival divided by the number of replications, which is 100. That's the equation. What is the message from this? If we get this result, what are you going to do? The message is you don't have enough replications because the standard deviation is almost something like 60 or 70% of the estimate of the probability of failure. So that's not enough. Okay, we can do 1,000 simulations. Okay, so I will not show the entire spreadsheet because it's big. The estimate now is 2%, 1.9%. Again, to assess the accuracy, the standard deviation is 4 per 1,000 or 0.5%. Okay, this is better than before, but still it's not good. You want something that is a little bit lower. And let's do 10,000. Or so the results for 10,000. So if you do 10,000, you find that the estimator of the probability of failure is 2%. The standard deviation is 1/10 of 2%. So the standard deviation is about 5% of the estimator. That's pretty good, right? Okay, you can make a figure that shows how the estimator changes with the replications. So the blue curve shows the estimator. We started from 10 and we got a 0 probability of failure. Then when we did 100 replications, the estimator of the probability of failure jumped to 3%. And then when we did 1,000, we found the probability of failure of 2%. And then when we did 10,000, we found the probability of failure of almost 2%. This is the spread between the two estimates. We have the probability of failure -1 standard deviation and the probability of failure +1 standard deviation. So this gap measures the accuracy. So you see that the gap narrows as you increase the replications, and here the gap is pretty low for 10,000 replications. Okay, so I would stop at 10,000 certainly. Now, can you predict how many replications you will need to refine your accuracy? Say that you have done 100 simulations and you got this probability of failure, and this is the gap between the two, the upper and lower estimates. Now, what happens if you want to reduce this gap to, say, 1/2? How many replications would you do? So you have done right now 100. You want to reduce the gap by 50%. How many replications do you have to make? Approximately.
It's about 4 times more.
Right, 4 times. Every time you want to reduce the gap to 1/2, then you have to do 4 times more applications. Okay? That's kind of a rule of thumb. Okay? Let's see another spreadsheet. This is when we do important sampling. Let me see if we can make it for standard. Okay, actually, this is something that we have to show later because we didn't cover the important sampling yet. So let's we'll do a kind of an example that is a little bit more complex with standard Monte Carlo. For example, reliability analysis of a simply supported beam. Here is the problem. We have a beam that is simply supported. This is the material here. There is a load, an applied load that is distributed over the span of the beam, and the load is Q. And this is load per length, okay? We also have axial forces. So we have an axial force, pair of axial forces. Okay. The beam has a shape of a T. So this is the geometry of the beam. This is a T-shaped beam. That's a cross section. And some dimensions. This is BF. This is the thickness. BF. This is the thickness W, and the height HW. The vertical portion is called the web. This is the web, and this is the vertical portion is called the flange. So we have a flange and the web. Okay. So let's define the problem. The length of the beam is 1.9 meters. The height of the web, this one, is 0.1628 meters. Okay, that's the height of the web. The flange, this dimension of the flange is 0.1392 meters. The thickness of the web is 5 millimeters, or 5 thousandths per meter, and the thickness of the flange is this. So these are the dimensions, and these dimensions are fixed. Assume that they are well controlled so that you don't have variation. Now, the random variables and then distributions. Random variables. The force, the axial force is normal with this mean value, 1.8 by 10 into the fifth, and standard deviation, 3.6 by 10 into the fourth newtons. That's the axial force. There is also this distributed force, which is normal with mean value 1.52 by 10 into the fourth power. The standard deviation is 3,000. And what are the units for a distributed load? Well, it's load per length, so it is newtons per meter. The strength, the ultimate strength is normal with this mean value and standard deviation, 5% of the mean value. This is newtons per meter squared, okay, this is pascals. This is for tension, okay? The material can also fail because of excessive compression, so we have to consider that also. So the compression strength is minus this variable, equal to minus S cubed. Okay? And we have also the Young modulus, which is another random quantity normally distributed. And standard deviation 3.5 by 10 into the 9th. This is also pascals. Okay. Let's look at the ways that a beam can fail. So failure modes. The beam in general can fail in different ways. So we have to check every different way. What are the failure modes? Well, the upper line can give either in tension, I'm sorry, the upper line would be actually in compression. And it's unlikely to give in tension, so you have compression of the upper line. So the first one is upper line give in compression. And this will occur if the strength, the applied stress is less than minus SU. That means this is a negative number for compressive strength, okay? So if you have a number that is even less than this negative number, you have failure in compression of the flange. Okay? Now the second one is that the bottom here, this will fail in tension. Okay? So that's another mode. Lower line here. In tension. And this will happen if the stress at the lower end, at another location, becomes greater than the strength. So now it is positive, and it's greater than the tensile strength. Okay? Let's make a sketch to solve that. If this is the cross-section of the beam, then the upper part is in compression or under compression. Okay? And this part is tension. So we have this point A that can fail in compression, and this part, this point B, that can fail because of excessive tension. There are more failure modes. One additional is excessive deflection. You don't want to have a beam that deflects too much. You don't want something that will deflect too much, okay? And the last one, there's another mode. What is that mode? What is another way that structures can fail? Buckling, right. And buckling occurs under compression, so you got to evaluate if the flange will buckle, or maybe even the web can fail. The upper part of the web may fail, okay, because this part is still under compression, so this part you may have local buckling. Okay, so Euler buckling. In the horizontal plane. And in the vertical. In terms of the excessive deflection, we have to define a limit, what is acceptable deflection and what is not. So excessive deflection if delta, the deflection of the midspan, is 1/2 of the total height of the beam. That's a given. Okay? So we got to calculate the deflection, and if the deflection exceeds 1/2 of the total height, then this is considered failure. And in terms of the, if you calculate the total height and you divide by 2, this is equal to 0.839 meters. So we got to check for all these failure modes. Okay. So let's do some calculations in order to have expressions for all the performance functions. So we have, in fact, we have 5 failure modes there, because we have Euler buckling in 2 ways, in 2 planes. So we got to have expressions that relate the random variables with this limit state functions or performance functions. Okay, the area of the cross section is df times df. So this is the area of the flange, the upper part, plus the area of the web. So this is 151 square meters. Okay, so that's the area. We want to find the neutral axis. So if this is the cross section, we want to find the neutral axis. Okay, the neutral axis, the height of the neutral axis is the width of the flange times the thickness times divided by the area that we calculated. So this is 0.12 meters. So the height of the neutral axis, the distance from the bottom, is 0.12 meters. Okay. We need moments of inertia. Moments of inertia in the horizontal and the vertical axis, so that we can calculate the bending stresses. So I will skip the equations and I'll give you the result. This is the moment of inertia about the horizontal axis. So this is x. The moment of inertia about this axis is 4.44 by 10 into the minus 6. And the unit is meters into the 4th power. Okay? That's the moment of inertia on the horizontal axis. On the vertical axis, it is 1.13 by 10 into the minus 6 meters into the 4th power. Okay? So that's the moment of inertia in the vertical, relative to the vertical axis. This moment of inertia are important to calculate, to check for buckling. Okay? You notice that the moment of inertia about the horizontal, about this axis, is quite bigger than the moment of inertia about the vertical axis. Okay? So we may have to worry more about buckling of the flange. Okay? And the reason that the moment of inertia about this axis is smaller is because the flange is shorter than the web. Okay. We need to calculate the moment, the applied moment in the middle. So M middle is, what is the equation for the moment? What it is? 2 times L divided by 2 times L over 4, and this is 2L squared divided by 8. That's a moment, the bending moment in the middle. If you use the equation My over I, you're going to calculate the stresses, okay, in the extreme fibers. If you want to calculate the stress on the upper part of this point, the stress is because of two components. One is bending. You have bending, so you have compression of the flange, but you also have the axial force that also causes a compressive force. So SA, the stress at the upper part, which is compressive, is minus the moment in the middle, which is this, times the distance from the neutral axis, divided by the moment of inertia, and then you have to add the effect of the compressive stress because of the compressive force. So this is a compressive stress. We have the stress, the tensile strength at the bottom. So this is B, point B, and we have a tensile stress. So the tensile stress is the moment at the midpoint times the height of the neutral axis divided by the moment of inertia. Okay? This stress, as we said, is compressive, also tensile, because we have the lower ply. Then we have another component that causes a stress at the bottom. What is that component? Well, yes? P over A, right, and it's compressive. It's a compressive stress, so you have to add that. Now, because it's compressive, it's negative, so actually it helps to reduce the strength. The total, the stress. So the total is tensile. Okay? So these are the stresses. Okay, let's check now, let's write the equation for yield. Upper ply yield is one failure mode. And this occurs when SA, at the stress at the upper point, is less than minus S2, okay? Now, less means that this is a negative number that is more negative than the strength. Okay, so this is negative. Okay, the lower lie yield tells you the stress at point B is greater than S2. Okay, so this is to check about yield. The excessive deflection delta max minus delta is negative. Now Euler backlink there are two critical stresses for the horizontal and the vertical plane. So for the horizontal plane, the critical value is pi squared in moment of inertia about the vertical axis over L squared. And then for vertical, L squared in moment of inertia about x divided by L squared. Okay. Any questions? So now we do Monte Carlo simulation. Someone has programmed solve these equations and checks the probability of failure. I'll give you only the summary. I did 1,000 replications, standard Monte Carlo simulations. Simulation generated random numbers for the loads. And here are the results. We have failure modes, the number of failures observed in 1,000 replications, the probability of failure, and the standard deviation of this probability of failure. Okay, we have to worry about 5 failure modes. Okay? No failures were observed for yield, or upper ply or lower ply yield. No failures for deflection. Okay. Backlink A vertical backlink, I found that it's also no failures for vertical backlink. Now that doesn't mean that the probability of failure is 0. It means that it's very small. And then for backlink in the horizontal direction is 197 failures out of 1,000 simulations. So this probability ought to be quite high. So the estimate of this probability is 197, and the standard deviation is 0.0126. Okay? So this is horizontal backlink. Okay? So looking at these numbers, what do you conclude? Well, the first conclusion is that if the system fails, it's going to fail because of horizontal backlink. Okay, that's the major conclusion. And so you got to do something with the floods. That's the problem. Now, does it make sense to do more Monte Carlo simulations when you reach this point? No, because you know that this design is unacceptable anyway. It doesn't matter if the probability of failure is 20% or maybe 15% or 25%. Doesn't matter. What you have to do is stop here and reinforce the design. That's the conclusion. One other conclusion is that there is a problem with a particular mode. The other modes show no failure, but this particular mode has high probability of failure. Is this design, if you have something that typically in real life there are a lot of failure modes, if one dominates like this, is this a good design? No. Or another way to say it is that there is a lot of opportunity for improvement, because if you reinforce the horizontal flange, for example, immediately this probability of failure will reduce a lot. Okay. So this is not a good, some conclusions that you can draw are this is not a good design. This is a bad design. Because you have high probability of failure. Okay? And the other is that you got to do something with the flange. So either increase the thickness or make it maybe longer, the flange. So increase flange dimensions. Okay, and we shouldn't do any more applications. It's a waste of time to try to become more accurate, because anyway the design is not acceptable. So do not do more applications. Okay, so accuracy sometimes is useful. This is an example where more accuracy is not useful, because you already know what you have to do with the design. Okay, any questions? So this finishes the discussion about standard Monte Carlo simulation, and now let's talk about more intelligent methods to do simulation. So we'll talk about variance reduction techniques. Variance reduction techniques. Variance reduction, we use the term variance reduction to say that these methods reduce the variance of the estimator of the probability of failure. Large variance is bad because it means less accurate results. So we are using an intelligent scheme to generate random variables to reduce the variance. That's what this means. Variance refers to the probability of failure. Okay, two methods will be discussed. One is important sampling, and the other is stratified sampling. The most common method is actually important sampling. So we'll talk about important sampling. So let's give some idea first about why we need important sampling. When the probability of failure is low, you need too many replications. When probability of failure is low, too many replications are needed. Okay, let's see a quantification of what you have to do, how much you have to increase the number of replications to reduce the variance. Okay, the equation for the standard deviation of an estimate of the probability of failure is this. Probability of failure times 1 minus the probability of failure divided by n. Okay, so you have this square root. If you want to express the standard deviation in terms of the probability of failure or as a fraction of the probability of failure, the standard deviation divided by the probability of failure is this. 1 minus the probability of failure, square root of 1 minus the probability of failure, divided by n times the probability of failure. Okay, that's the expression that we have for the coefficient of variation. Now, if you want, at a minimum, you want, in order to have good accuracy, you may want to have a coefficient of variation of 10%. So the standard deviation is 10% of the probability of failure. Okay? So standard deviation is 10% of probability of failure. Okay? Then you can find an equation about how many replications you need. How do you do that? Well, you put here 0.1, okay? So 0.1 equal to square root of 1 minus the probability of failure divided by n times the probability of failure. Okay, So let's solve for n, okay? So you have the number of replications needed for a given probability of failure. Well, if you solve that equation for n, then you have that n, the number of replications required to have a 10% coefficient of variation is 100, 1 minus the probability of failure divided by the probability of failure. Okay, that's the equation that you can use to predict how many replications you will need. So let's make a table to see how the probability of failure influences the number of replications that you need to estimate it. Okay, if the probability of failure is 1%, then you need 9,900 replications. Okay, almost 10,000. If it is 1 per 1,000, this is almost 100,000. If it is 1 per 10,000, then you need 1,000,000. Okay, so this is a problem because you don't want to analyze 1,000,000 beams to find what fraction fail. Okay, that's not good. All right. So that's why we use important sampling to reduce that number. So the idea of important sampling is to use a sampling distribution that is different than the true one, and it causes more failures. And then you scale every failure by the likelihood to observe that, the likelihood ratio. So idea, use a sampling PDF. F subscript S, so that many failures occur. Okay, then you scale every failure by the likelihood ratio. Likelihood ratio is the ratio of the true probability density function of the variables over the sampling. Okay? So scale failure according to the likelihood of each sampling point. Okay, so you don't count failures, you count actually failures scaled by the likelihood ratio. So as a concept, to explain the concept with a sketch, we have here an example with an applied stress in the strength. And then here we have the density of the stress and the density of the strength. Now, the density, the true density is this. The true density of the stress is this. Okay, so this is F of S, the true one. If you generate points, will be anchor points like this. Now, if the strength is here, then you don't have a lot of values. You don't have values in the interference region. So instead of that, you use another sampling distribution so that it generates a lot of points in this region. So these are sample points from the sampling PDF. Okay, you have many failures, so computationally this is good because it will give you a more accurate estimate. Okay, now as we said, you don't just count the failures and find the frequency of failures because that is a biased estimator. So you got to correct the bias. Okay. So let's see in standard Monte Carlo simulation, the estimator. The estimator is EF equal to 1 over the number of replications times a counter function that is the values of a failure counter function, okay, or failure index function. This is for standard Monte Carlo, but doesn't apply if you use samples from another distribution, okay? If you want to estimate the probability of failure, if you use these red points, the points that represent the sample values from the sampling distribution, then you use this estimator. This is the sampling PDF. Okay, and this is the true PDF. Okay, so what is this ratio in this example that we saw here? The ratio of the two probability density function. Is it large or small?
Small.
It's going to be small. And the reason is that all these points, if you calculate the PDF, the true PDF, they have very, very small PDF. Okay, because they are in the tail. And they are very, very unlikely to occur. So this value is small. So you are dividing a small value by a large value. So that actually makes the estimator unbiased. Okay? This estimator is unbiased. Okay? Any estimator should be unbiased, What does it mean, unbiased? Well, empirically unbiased, something that is not biased towards high or low values. It's just accurate, okay? But if you want to be more precise, it means that if you calculate repeatedly this estimator, doing a lot of repeated simulation, on average, these values will be exactly equal to the probability of failure. Okay? They're not going to be bigger or smaller. Okay? So this is unbiased. Any estimator should have that property. Okay? So this is on average is on target. Or if you calculate the mean value of this quantity, the mean value is actually the probability of failure. If you calculate that mean value, okay? All right, let's stop here and we'll continue with the important sampling method next week.